Conakry is the largest city and the capital of the country of Guinea, and it has possibly the most interesting geology of any capital in the world. The entire city stretches around 25 miles from the southwest to the northeast, on a peninsula that never gets more than 4 miles wide. The reason for Conakry's confined city is because of barriers on all of its sides. To the west, we have the Atlantic Ocean. To the east, we have the sharp cliffs of the Fouta Djallon Peninsula. And to the north and south, we have dense mangrove swamps. All of this geography has acted as natural barriers, preventing Conakry from expanding. So in today's video, let's explore the geology of Conakry and the surrounding regions. The original city of Conakry itself began as a small settlement on an island. This island is named Tombo Island, and it is where the modern-day downtown of the city is still found. However, today, Tombo Island has been artificially connected to the nearby Kaloum Peninsula by a small causeway. Looking at old maps of Conakry, you can see how it was once on this island. This is a map from 1893 that clearly shows the separation between Tombo Island and the Kaloum Peninsula. So how did Tombo Island and the Kaloum Peninsula form? And why is it much more habitable than the surrounding terrain? Well, to answer that, we have to go around 200 million years ago. During this time, the supercontinent of Pangaea had just begun rifting between North America and Africa. Continental rifting is primarily caused by mantle plumes, where large areas of magma plume up towards the surface and causes two parts of continents to rift apart from each other. In the case of Pangaea here, these mantle plumes not only rifted apart North America and Africa, but also created a large amount of igneous rock, known as the Central Atlantic Magmatic Province. This magmatic province, or igneous province, is the largest continental igneous province in the world, coming out to be around 11 million square kilometers. And it created igneous rocks stretching from modern-day South America into Europe. One of the areas created by this continental scale magma plume was our Kaloum Peninsula and Tombo Islands. The specific formation that formed the Kaloum Peninsula and Tombo Island is known as the Conakry Igneous Complex. This igneous complex formed near the beginning of the Central Atlantic magmatism. It formed around 200.4 million years ago. And these rocks are specifically an igneous intrusion, where magma intrudes into older rock and hardens, creating regions of igneous rock within the older pre-existing rocks. However, in the case of our Conakry igneous complex here, it did not form in any random location. Instead, it formed along a much older formation, known as the Conakry-Dalaba lineament. A lineament is essentially a region of landforms that are associated with underlying weaknesses, specifically faults or fracture zones. So in the case of our Conakry to Dalaba lineament, you can see how the faults have created these many straight line valleys. And it is along one of these fault lines that the Conakry igneous complex initially intruded into. This is the reason why Conakry is so much longer than it is wide. It is because it formed along a mostly straight line fault. So once magma intruded into one of these faults around 200 million years ago, it formed the Conakry igneous intrusion. The specific type of igneous intrusion here is known as a mafic to ultramafic laccolith layered intrusion. Now I know that was a lot of terms, so let me break it down term by term. The mafic to ultramafic refers to the type of magma and igneous rocks that intruded into the fault line. So if you were to look at the rocks of Conakry, you would find mafic to ultramafic rocks such as wehrlite and dunite. The laccolith part of the name refers to the shape of the igneous intrusion. In this case, it is a dome-like shape, where the magma first spread outwards and then was built up like a dome. Today, the Kaloum Peninsula is a ridge, and this ridge represents the dome of the laccolith. And finally, we have the layered intrusion, which refers to how the intrusion formed, or the type of igneous intrusion. In this case, the Conakry igneous complex formed as 3 different units, each with their own unique property. Units 1 and 2 are associated with the green on this map and form the vast majority of the Kaloum Peninsula. It is also important to mention that despite this being called a layered intrusion, there are not clear layers within the rocks. It is simply called a layered intrusion because 3 different stages of magma formed the intrusion. Next we have Unit 3, which is the blue on this map. This unit actually intruded into the 2 previous units. This Unit 3 formed Kaloum Mountain at the northeastern end of the Conakry Igneous Complex. Unit 3 is composed of more resistant rocks than Units 1 and 2. Specifically, it is composed of rocks known as gabbros. This has made it more resistant to weathering and has left the mountain standing today. After the peninsula was formed and exposed to the surface, one more process happened that made the land appealing to settle on. This is the creation of something known as a ferrocrete. Ferrocrete is essentially a cemented layer of soil that is rich with iron. This ferrocrete forms and builds up over the many millions of years of rainwater falling onto the region. This rainwater mixes with the soil and then cements itself into the layer of ferrocrete. This layer of ferrocrete is one of the primary reasons that Conakry was settled. And in fact, the 1950s actually saw a huge population boom associated with this iron mining. So to recap, the physical city of Conakry lies on a 200-million-year-old igneous intrusion, which intruded upon an old fault line. This igneous intrusion created an area of higher ground and a thick layer of iron that both made it appealing for settlement. But now that we've talked about the Kaloum Peninsula and Tombo Island itself, let's talk about some of the surrounding terrain. If you have been looking at the maps, you have probably noticed the fascinating archipelago located to the southwest of Conakry. This archipelago, which almost looks like a location from Sea of Thieves, are known as the Los Islands. Today, the Los Archipelago consists of several different islands. Specifically, we have Tamara, Casa, Room, Corral, Blanche, and Cabri as the primary 6 islands of this archipelago. So how did these islands form? Well, they actually have a geologic history which took place nearly 100 million years after the Conakry Igneous Complex. Specifically, these islands formed around 104.7 million years ago. This is a time associated with the continued rifting apart of Pangaea, more specifically the rifting apart of Africa and South America from each other. Now, much like our Conakry Igneous Complex, the Los Archipelago are an igneous intrusion. The Los Islands here formed on a passive margin, which means that there was no subduction occurring in the zone. However, that by no means implies that there was no magmatism in the region. You see, much like the Conakry Igneous Complex, the Los Archipelago is said to have formed within an old weakness in the crust. However, this is not actually the same weakness. It isn't the Conakry Tadalba lineament. It is instead the much older and continent-spanning Guineo-Nubian lineament. This Guineo-Nubian lineament, named GNL on this map, is said to have been reactivated due to tensional stress, or the pulling apart of 2 sides of crust, associated with the rifting apart of Africa and South America. This reactivation of the lineament caused magma to be able to break through and form a volcano where the Los Archipelago is today. If you saw my Oland Islands video, you probably have an idea on what type of igneous intrusion these islands represent. That being a ring dike intrusion. If you missed my Oland Islands video, a ring dike intrusion usually forms after the eruption of a volcano. However, in the case of the Los Islands here, they actually formed from a more gradual draining of the magma chamber. This gradual draining caused a central block, known as the roof block, to slowly sink down into the magma chamber. Then, magma filled into the ring fault, and it solidified into igneous rock. In the case of the Los Islands, the primary rock here are a rare igneous rock known as nepheline syenite. However, this nepheline syenite varies in how alkaline it is, and this suggests that instead of one magma pulse, there were actually multiple pulses of magma. For a more in-depth overview of the geochemistry, there is a very detailed source in the description. So that is how the outer islands formed. These outer islands represent when magma intruded into the ring fault line. But how did the central Room Island form? This Room Island formed in one of the final pulses of magma, During this pulse, the roof block fractured in the middle and allowed magma to seep into the center. Not only did this solidify and create Room Island, it also created a series of radial faults emanating from the center of Room Island. Radial dikes are very thin intrusions that emanate from a certain point. So for example, here is a grouping of radial dikes in Colorado. Each of these lines represent one of these radial dikes emanating from the center. So this is how the Los Islands formed. This Los Archipelago undoubtedly needs to be studied more. The primary source I found on it mainly talked about the geochemistry of the islands. But overall, these Los Islands are a very unique formation, and definitely look like a location that would be found in Sea of Thieves. Finally, let's cover the geology of the two things preventing Conakry from expanding outwards. The first of these are the Guinea Highlands, more specifically the Fouta Djallon Plateau. The Fouta Djallon Plateaus are composed of a wide variety of sedimentary rock. The rocks surrounding Conakry specifically are known as the Pita Group, which are rich in quartz. The Fouta Djallon, and thus the Pita Group, formed during the Ordovician period, which lasted from 485 to 443 million years ago. The plateaus formed outwards from the Man-Leo Craton, a more than 2 billion-year-old craton that still comprises the bedrock of a lot of this West African region. These plateaus represent primarily alluvial or river-driven sediment. Over millions of years, the river moved quartz-rich sediment from the Man-Leo Craton into a basin known as the Bove Basin, and this would build up the quartz-rich sedimentary rock of the Fouta Djallon. But the final step of creating the plateaus as we know them today is the erosion and further uplift. These plateaus uplifted in a process known as epirogeny. Unlike a typical orogeny, which is found when two tectonic plates collide, an epirogeny is caused by a change in the convection of the mantle. What this does is cause a large section of the crust to uniformly rise or sink. This epirogeny process occurred in our Guinea region and caused the Fouta Djallon to rise higher than surrounding terrain. Next, there is the differential erosion. The Pita Group, as I mentioned before, is composed of sedimentary rock that is rich in quartz. These quartz-rich rocks are more resistant to weathering than the surrounding rocks, creating these sharp cliffs and large plateaus. As I mentioned earlier in the video, these lines that pattern the Fouta Djallon Peninsula formed as a result of the Conakry to Dalba lineament. So all of these lines you can see today represent old weaknesses in the crust of the Earth that have now been expressed on the surface. The Fouta Djallon today, with its sharp cliffs and rocky terrain, act as a natural barrier that prevents Conakry from expanding. However, this plateau actually serves as one of the world's largest sources of bauxite. Bauxite is the primary source of aluminum and gallium, and this makes the Fouta Djallon very valuable to Guinea. In 2024, exports of bauxite reached around 137 million tons. So despite the plateau seeming like a feature preventing Conakry from expanding, it is actually very valuable to the country of Guinea. Finally, to the north and south, we have the Guinean mangroves. To the north, we have the Dubreka and Conakry estuaries. And to the south, we have the Tibunsu estuary. These estuaries lie on top of an old coastal plain formed by river sediment. During the Ice Age, when the sea levels were much lower, these rivers were able to build the coastline outwards towards the ocean. However, after the glaciers melted, the sea levels would rise, drowning the river valleys and creating the estuaries that we can see today. If you watched my classification of river deltas video, then you may think that these are tide-dominated deltas. However, this is actually not true. The estuaries surrounding Conakry do not have the sediment output to be considered deltas in the first place. These estuaries prevent Conakry from expanding because of the complicated network of muddy mangrove channels. However, this mangrove ecosystem is very important for the native wildlife and industries like fishing. Unfortunately today, large areas of these mangrove swamps are being cleared for both agriculture and the city's expansion. Some mangrove swamps, primarily around Conakry, are protected by a program known as Ramsar. However, there is still a large amount of mangroves being cleared in the area. In today's video, I covered the fascinating geology of Conakry and the surrounding regions. Conakry lies on an old igneous intrusion that creates an iron-rich ridge perfect for settlement. Around Conakry, we have another volcanically formed archipelago of islands. And preventing Conakry from expanding are the plateaus of the Fouta Djallon and the Guinea Estuaries. However, despite these two features preventing Conakry from expanding, they are still vital for both the industry and ecosystem of Guinea. If you learned something new in this video, be sure to subscribe. And if you have any video suggestions, leave them in the comments below. But I will see you guys in the next one.